All right, so last time we talked about Bitcoin fundamentals, Bitcoin blocks, and wallets. Now it is a good time to talk about transactions. Then I will talk about forks and mining so that we will conclude our discussion about Bitcoin. And understanding Bitcoin will actually help you to understand almost every cryptocurrency. So since Bitcoin is the first one, then we can talk about the others and see what are the differences, okay? So let's talk about transactions. A transaction can be in either one of the two states, spent or unspent. This is actually valid for almost every cryptocurrency. So once you transfer Bitcoin ownership to somebody else, when you look at it at the blockchain, next to it, you will see that it is either spent or unspent. So once it is spent, actually, you don't need to deal much about it because it's spent in the future block, so you don't need to look at this previous transactions. You cannot spend part of a transaction. This is very important. In some cryptocurrencies, maybe you can, but in Bitcoin, you cannot. Okay. In theory, a transaction can be performed without a fee because actually a transaction takes an input and output. So in your input, maybe it's 4 Bitcoins. So if your output is again 4 Bitcoins, since you subtract them, the result is 0. This means that actually you are not paying any fee. So in theory, you can do it, but in practice, none of the miners will accept that, okay? So in practice, people expect at least 1 Satoshi per byte. So we call this a relay fee. So this means that nodes will not notify other nodes about transaction with fee less than 1 Satoshi per byte. So 1 Satoshi is this many Bitcoins. So 0. I think there are 8 decimals here. So, and in some cryptocurrencies, this is even larger. For instance, in Ethereum, you will see many zeros here. I think the smallest value there is Wei, but in this case, we have 1 Satoshi. So whenever you want to make a transaction, you are connected to the blockchain network, either by a full node, maybe you're a full node, or maybe you're just using an application on your mobile phone. So it is actually a light node, so it tells other full nodes that you want to make a transaction. So you announce your transaction to the people that you are connected to. So now you don't connect to everybody in the blockchain. Generally, there are 10,000s of nodes. You don't tell every one of them that you want to make a transaction, okay? You simply tell a few of them which you are connected to. So once you tell them, they relay it to other nodes. But if your transaction fee is less than 1 Satoshi per byte, those nodes most probably will not relay your message. So actually, in practice, you cannot make a transaction without 0 fees, okay? So you have to actually determine a fee. And in the following slides, I will show a screenshot from a time where paying like 3 or 4 Satoshis per byte is enough to be included in the first block. If a transaction has been sent with a very low or 0 fee being offered, it can be ignored from the next block and perhaps the next block and so on. So if you pay a very small amount of fee, maybe your transaction will be valid maybe in the following days, but not that instant. This is why people prefer to pay more fees if you want to make that transaction as soon as possible. So in theory, what we are doing is that Alice actually transfers Bitcoin to Bob. So actually, Alice transfers the ownership of her coins to Bob. So Alice does the following when she wants to make a transaction. To prove the ownership, Alice includes script seek to her transaction script. So transaction script actually is the script where she transfers the ownership to Bob. And Alice signs it is, so this way she proves that she actually owns it because she has the private key. This is where the digital signatures come into place. So actually she proves that she owns it and says that now it belongs to Bob. Actually, she doesn't tell the name Bob, but only gives the wallet address. So actually making a transaction means that I own this many Bitcoins and I transfer the ownership of them to somebody who has the private key to this wallet address, and that's it. So the person you are transferring the Bitcoins to don't have to be online. As long as they have the private key to that wallet address, they can connect to network whenever they want and, you know, do whatever they want with that money. So the script part is actually called unlocking part. So Alice actually unlocks her Bitcoins. Then she transfers it to ownership to Bob. And her transaction includes Bob's public key, which is called secret pub key. So here she locks it again. So she has some Bitcoins, she unlocks it by proving that they belong to her, and she transfers to Bob by providing this secret pub key. So this is the locking part. So we talked about this before. As you can see, you do not receive cryptocurrency like in the physical sense, right? Actually, all of the cryptocurrency written on the blockchain, and we record who that Bitcoins belong to, right? By putting the public key or the wallet addresses. So whenever you want to transfer it to somebody, you actually prove that you own them and transfer the ownership to somebody else. So this is why in your wallet software, you don't actually have the coins in your laptop or your mobile phone. It is on the blockchain. So this is now this might be obvious, but a lot of people have misconceptions about this. So whenever you announce the transaction, we said that people, all full nodes actually transfer to other people. So every full node user of the blockchain needs to be notified that a transaction has taken place. To simplify the process, you just need to tell a small selection of nodes that your Bitcoin client is connected to. And actually, if you use Bitcoin Core, you can just click some buttons and see which IP addresses you are connected to, okay? And for the Bitcoin Core, the software uses the port number 8333. So this way, listening to that port actually or other IP addresses, you can see what the network is doing, okay? These nodes in turn tell the nodes they are connected to and so on. So whenever you hear a transaction, if you're a full node, maybe you hear it from the person who wants to make the transaction, but maybe you are in the fifth or sixth hop. So maybe the person who announced it connected only to few nodes, they connected to other few nodes, and so on and so forth. So you cannot be sure who is making the transaction by looking at the IP address that you hear the transaction from, okay? This is very important. Some forensics analysts think that whenever they hear a transaction from an IP address, they think that that IP address is making the transaction. So whenever they want to follow the money, they make wrong decisions because of this, okay? And it might be possible that the person who wants to make the transaction is using a Tor network. So maybe they're behind the Tor network. So whenever you see the IP address, maybe it is just Tor exits node, okay? So it may not belong to the person who wants to make the transaction. So we mentioned that whenever you want to make a transaction, you announce it to every node. So now every node knows it, but it is not included in the blockchain because we haven't written it in the block yet. And when we talk about mining, we will talk about how we do it. But currently, you just announced it. Everybody, all of the full nodes know it, so they write it to the mempool. So this is a screenshot from this web page. As you can see, here they say that the relay fee is 1 Satoshi per byte. So if you offer anything less than this number, the nodes will not relay your transaction message to other nodes. So you cannot make a Bitcoin transaction paying less than this many. So since you pay per byte, having a small transaction size would be better for you because you would pay less fees, right? This is why we actually have some updates like SegWit update and so on. Here, if you visit the web page, you will also see what happened in the recent blog. So I took this picture probably a few weeks ago. So as you can see the block height, how many transactions it includes, and how many bytes that block consists of. And here, as you can see, there are many zeros here. So this is the solution of the hash puzzle. So as you can see, we said that the Bitcoin block size is 1 megabyte, but here all of the blocks actually exceeds 1 megabyte, right? This is why we mentioned the SegWit update, and in the fork section, I will talk how this happens, but virtually this number can increase to 4 megabytes if we have very compact transactions, okay? So in the web page, you will see a picture like this. This picture actually goes below, so there are many rectangles in this picture. I only take the screenshot of the top part, and these are actually transactions that are waiting to be included. So actually this explanation is very good, so let me read it with you. Mempool contains a list of client-validated transactions that have yet to be included in a block. Table below shows addition and eviction of transactions from the mempool during the last hour. Black bar at the bottom of each cell indicates size of the transaction against average bytes, and darker backgrounds indicates a lower than average fee. So these darker ones paying lower fees, so it will take more time for them to be included. And the bars here actually indicate the size of transaction, okay, against the average bytes. So average bytes and average fee in Satoshis per byte are calculated based on transactions from the last hour. Smart fee in Satoshis per byte is calculated based on estimate provided by estimate smart fee command for transaction to begin confirmation within 6 blocks. See also here for the unconfirmed transactions. So as you can see, the average fee is 3 Satoshis per byte for the time I took the screenshot, of course. If the network is not that busy, this number might be smaller. If it is very busy, it might be higher. Actually, I haven't checked today, but since there are many activity today, maybe these numbers might be higher today. Okay, so we can check at the end of the lecture. But if you pay 4 Satoshis per byte, this means that most probably it will be included in the first block that the full nodes hear your transaction. Okay, so this is actually how it works. You say that you want to make a transaction. It is included in this kind of mempool, and full nodes include them by solving the mining puzzle. Okay, so this will be more clear when we talk about mining. So let's talk about different types of transactions. So main type of transaction is just, transferring Bitcoins to other people, right? So we talk about pay to script hash, and I told you that people use this for multi-signatures and take the hash of the multi-signature script, but this doesn't have to be always this way. I told you that anything that you write a script for can be included here. So you can create many different scripts. So I like this script, which is actually referred to as SHA-1 collision bounty. So Peter taught offer rewards for SHA-1, RIPE-MD 160, and SHA-256 collisions by transferring Bitcoins to a pay-to-script hash accounts, which can only be claimed by providing collisions. So he wanted to promote people to try to find collisions to see if these hash algorithms are secure. So in 2013, he created for all of them a pay-to-script hash and transferred money to this wallet address. But anybody who has a collision can withdraw it. So nobody owns the public key for that wallet address because it doesn't have a public key. The script actually works whenever you provide a collision. So let's look at how this works. So the pay-to-script hash result for this SHA-1 bounty is this. As you can see, it starts with 3. So this is pay-to-script hash address. So this hash actually belongs to a script where the owner can claim it as long as they provide a collision for SHA-1. So this was a challenge in 2013, and this is valid for all of the others. But since we have a collision for SHA-1, let's see what happened to this. So if you want to look at the transactions for this wallet address, you can go to blockchain.info. And many people transferred Bitcoins to this address to promote people to, encourage them to try to find a collision. So this is actually the disassembly of the script for this collision. So it's full of opcodes. As you can see, let's look at 2dup. equal, not, verify, SHA-1, swap, SHA-1 equal. So this is the script. And this actually tells you that if you can provide collisions for SHA-1, you can, perform transaction for this address. So let's look at this in detail. So as an input, you have to provide two things, right? Since it is a collision, you have to put two different inputs and they should give the same SHA-1 output, right? This is what we call a collision. So you have two different inputs and their SHA-1 results are the same. So let's look what happens. So if somebody as the input provides A and B, claiming that these two non-different, not equal values has the same SHA-1 hash, they have to try to, put these values as an input and see if the script works. So op2dup duplicates the last two elements on the stack. So AB becomes AB and AB, right? Then what they do is that they check if the last two values compare if the top two elements are equal. Because if they're equal, then you are cheating because you're providing the same values to show that they have the same SHA-1 output, right? But the SHA-1 collision means that the input should be different. So this part actually is for there. If they are equivalent, then the script will not run, okay? But if they are not, then you run the op verify code, because if they are not equal, this code remove the results and continue the processing. So if they are not equal, you will get false here, and this op verify will remove it. And at this stack, you will end up with A and B again. So next code says op SHA-1. So this actually computes the SHA-1 of the top element of the stack. So your stack becomes A and SHA-1B. Then op swap swaps the top two elements. It becomes like this. Next command is op SHA-1. So this way you calculate the SHA-1 of A. Then the next code is op equal. So you compare the results. If it returns true, then you claim you prove that you own this script. That is the idea. So this way you can spend it. So it was an open problem for a long time, as you recall, but in my lectures and also in this lecture, I told you that the first freestyle SHA-1 collision was found in 2015. So this is a collision. As you can see, this is a message M1 and this is M2. As you can see, they are different. For instance, this one starts with 9D and this starts with 3F, and both provide the same output. So this is a SHA-1 collision, but we say that this is a freestyle collision because if you look at the IVs here, they are different. For instance, here you have 90 and you have 91 here. This is why we call it a freestyle. Normally, when you use a hash function, the IV is fixed and you use that same IV forever, okay? Here, actually, the founders of this collision changes the IV because they work with a very small amount of GPUs. They run it for months and obtain this. And here they prove that if they had more GPUs, instead of restart collision, they will find the real collision. And they were right. What's IV? IV is, if you go back to our hash definition for SHA-1, if you look Merkle-Damgard construction, we divide our input into message blocks in SHA-1, the size, I think, 512 bits. So for the compression function, which is SHA-1, this message block is your first input, but second input is IV. And IV is fixed. If you go to NIST documents or any other standards, you will see that there is a fixed IV there, and everybody is using that, and Bitcoin also uses that, okay? So for the first SHA-1 message block compression, your inputs IV and the message block 1. So you produce an output, which is a compressed version. For SHA-1, this is a 160-bit value. If you have a second message block, now this value acts like the IV for the second part. So since this is a serialized process, it should start with a value, and that is why we call an IV. So as you can see, there are IVs here. If you use software like OpenSSL or something, you can choose your IV for using SHA-1, SHA-2, or anything. Okay, but in practice, you have to look at the standards documents because you don't want to ask for an IV all the time. So this is why you fix it, and in this documents it is fixed. Okay. So let me read the last bullet. A free start collision breaks the inner layer of SHA-1, does not directly translate into a collision on the full SHA-1 because the attacker is not able to choose the initial internal state, right? You cannot modify the IVs. So in 23 February 2017, Mark Stevens this time worked together with Google because Google said that they had a lot of GPUs. They didn't provide the exact number. Even I think Mark Stevens don't know it, as far as I know, but they said that they have a farm. Just write the code and modify it to run for this farm, and this way we can obtain a full collision. And this is why they announced this full collision using the GPUs of Google. As you can see now, the IV here and here are the same, but this time the collision is for 2 blocks, 2 message blocks, and the colored parts are the differences. So it is kind of a differential attack. Okay, so you find the differential collision here. So again, now that somebody found it, question is, can I use it to, solve the Bitcoin SHA-1 collision bounty? The answer is no, because this IV again is not the IV that is used in the standards. But now the question is, can I put a prefix to this collision so that if I can put a message block here and use the original IV and obtain the collision again, this would be enough to claim the rewards, right? So now your aim is to find a prefix to this collision. And since this is announced in 23 of February, those people who look at the blockchain realize that at 3 days later, somebody withdrew the money from this challenge. And what they did was as follows. The solution adds 3 identical blocks to the beginning of the 2-block SHA-1 collision and obtain this hash. Okay. So this is different than this hash result here, this collision. So what they do as follows. So they take 2 messages A and B, and first block of A and B, I write it as A1 and B1. I took this from the Bitcoin blockchain, by the way. So I don't know if you can see it, but these 2 blocks are identical. So they start with the original IV. The first block's like this. Second block, again, identical. Third block is identical. Now here, there is something different. And as you can see, this one starts with 7F. This one starts with 7.3. If we go back, as you can see, 7F is here and 7.3 is here. So they are using this block for A4 and B4. And for A5 and B5, as you can see, it starts with 30 and 33C, and it is here. So once people announced this collision, somebody tried to find a prefix for it and, solve the problem, and they earned 2.48 Bitcoins by solving this collision. So if you transfer anything to this address, you can use this collision again and withdraw it too. But the person who is fastest will withdraw it. So now everybody knows the solution to this problem. Everybody can withdraw it. So if you go to this address, you will see that I think thousands of transactions were made to this address. People, added small amounts of Bitcoins, which total to 2.48. But at this date, somebody withdrew all of them. So this is a very different way of transactions, as you can see. So far, people always think that Bitcoin blockchain only works for transferring Bitcoins, but nobody think that you could write this kind of scripts. So here is a good example. So the same bounty is valid for other hash functions like RIPE-MD 160 and SHA-256. Also the doubled versions of them. If you can find the collision for double SHA-256, you can also, there's a reward for that. But finding for the 2 application of SHA hash function is harder to find a collision for a single application of a hash function. So your first bet probably will be to find a collision for RIPE-MD 160. But I think the award right now 0.4 Bitcoins or something, so it might not be that appealing right now. But still, if you can find a collision, you can earn an extra money by withdrawing these rewards. Okay, something we haven't talked about was the transaction lock time. This is generally referred to as unlock time. So Bitcoin has a transaction level time lock feature since the beginning. So Satoshi put this feature. Not everybody is using it. Actually, almost nobody is aware of it, but you can do it. And actually, if you want to do some smart contracts and so on, you can use this feature. So transaction lock time is a transaction level setting, a field in the transaction data structure that defines the earliest time that the transaction is valid and can be relayed on the network or added to the blockchain. So it is set to 0 in most transactions to indicate immediate propagation and execution. So whenever you actually transfer Bitcoin to somebody, you choose unlock time equals to 0. But if you put a number here, then if this number is below 500 million, this means that it is interpreted as a block height. So actually meaning the transaction is not valid and is not relayed or included in the blockchain prior to the specified block height. So it will not be written to the block unless that block number is reached. Okay, so you're actually giving a limit there. But instead of saying which block height, you can also say at which date, at which hour it should be included. So this way, instead of writing a number below this, you actually write something above it, and it is interpreted as Unix epoch timestamp. So you actually write in seconds at which date this transaction will be valid. Okay, so a transaction with unlock time can be double spent before the lock time. This is the important part. So whenever you say you sign a transaction saying that this transaction will be valid after this block, and before that block height is reached, you can spend it so that that transaction becomes invalid. This is because, for instance, if you want to buy something from somebody physically, you actually do this payment by saying that it will be valid in the future, and you wait for the goods to come to you. So if that person is cheating, you don't receive the goods, then you, instead of waiting for that transaction to happen, you transfer that money to an account that you own. So you double spend it, so that your first transaction will become invalid, so that this way you can actually, recover your Bitcoin. So this approach can be used to, have smart contracts, but compared to smart contracts in Ethereum, here the smart contracts will work like in 2 transactions, where you, transfer the money, and in the second one you wait for that thing to happen, and it depends on what you're actually doing with that person. Okay, and also you can use multi-signatures and have a third person to decide which person will receive the money or not. So let me show you 2 pictures to finish this part. I actually mentioned this in the rogue part previously. So I said that you can actually hide messages in the blockchain, and there are many weird and bizarre messages written in the Bitcoin blockchain. And here is an example. We mentioned the block 666,666 because there were some vanity addresses like here. As you can see, this one starts with God, and this one starts with Bible. But as you can see, the output here have 3 addresses, right? 3 outputs. So 2 outputs, money is transferring to these 2 addresses, and as you can see, it is spent. So in the future, somebody withdraw this money from these accounts and transfer it to someplace else. Okay, but here is a third output, and here it starts with op return. So once the miner see the op return, it's just stops processing anything after that op code. So here you can write anything in hexadecimal. So this way you actually can put any message in the blockchain. But of course, the length of your message here increases the length of your transaction, so you pay more fees, right? So you want to keep it small, and there's also limits. I think you cannot exceed 512 bytes, if I'm not mistaken, but this is something we need to check because it sometimes it might be changing a soft fork and so on. But here the hexadecimal message here, if you copy paste it into any hexadecimal to ASCII converter, here you see that it is an quotation from the Bible. So this way, actually, you can find many hidden messages in the blockchains. Previously, this op return technique wasn't used, so people were actually burning bitcoins by transferring to an invalid address and then put the message there. But with the op return, as you can see, the value is 0 here. So 0 bitcoins transferred to this nonsense. Okay. So this way you can add messages to blockchain without paying much fee.